Can everyone see the whiteboard?
Yes.
Okay. Let's start with the first question. What answers did you get? Okay, good. 4 is the right answer. Pavan, can you explain?
Okay. So what I wanted to do first was, the goal was to try to cancel as many terms as you can because we wanted to see if they're divisible by 8. So I realized that 3 to the 0 plus 3 to the first plus 3 to the second plus 3 to the third, that equals 40, and that's divisible by 8. And every other factor after that is also going to be some multiple of this. So since there's 4 terms, we just basically group everything in 4 starting from the end. So that leaves us with only 3 to the 0 plus 3 to the first.
Good. Yeah. So this works. So you can kind of group things into 4, and you see that 4 of them are divisible by 8. So another way you can also look at it is, let's try to look for a pattern. So what is 3 to the power 0? When I divide it by 8, what is the remainder?
1.
Yep. What about 3 to the 1?
3.
Good. And then after this, what do we see the pattern to be? So if I do 3 squared.
1, 3, 1, 3.
Good. Yeah. So the same thing you can see by doing 3 squared, the remainder would be 1, and so on. So basically then, if you add up the remainders when you divide by 8, you would be adding 1 plus 3 plus 1 plus 3 plus so on, up to whatever 2009 should be. So this is a total of, it's a even number of total things we're adding, right? From 0 to 2009. So it'll end with plus 1 plus 3. And then we want the remainder of this divided by 8. So we see this is basically 4 times 1005, if we look at the number of pairs, and the remainder of this one divided by 8. So 4 times 1004 divides evenly by 8. There's just one remaining 4. So either way, you can see that 4 terms add up to a multiple of 40 and use that pattern, or you can just go by each element here and say 3 to the power 0, its remainder by when divided by 8, and so on. That makes sense? Any questions on this? Okay, let's move on to the second.
What did, for the part where you go 1 plus 3 plus that line, can you explain that line one more time?
Sure. So if we want the remainder of 3 to the power 0 plus 3 to the power 1 up to 3 to the power 2009 when divided by 8, right? We can also just take the remainder when dividing each of them by 8 and add it up, and then take the remainder of that when divided by 8. So in this case, we can look at, so for each term, 3 to the power 0, if I divided that by 8, I would have remainder 1. It's essentially, you can think about it as removing all the multiples of 8, looking at the remainders, and then seeing that the total of those remainders, and again, see how many 8s can I remove from that, essentially. So 3 to the power 0, we know the remainder is 1. 3 to the power 1, remainder is 3. We can do 1 by 1, right? So then we want to add up for 3 to the power 0 plus 3 to the power 1 up to 3 to the power 2009. What are all the remainders? So we can see it should alternate this pattern, 1, 3, 1, 3. So if I do 3 or 4 more here, you'll see the pattern continues. So 1 plus 3 plus 1 plus 3 up to 3 to the power 2009. So if it alternates, each pair will add up to 4 for 1005 pairs. Does that make sense?
Yeah, thank you.
Any other questions? Okay, let's go on to the second question. Okay, good. 12 is the right answer. A lot of correct answers here. Okay, Ishan, can you explain?
Yeah, so I just drew like lines to graph them.
Mm-hmm.
So the first point was -5 and 5.
Mm-hmm.
So, and next point was 2, 6. And the next point was -2 and 2. So I just like found out each side. So for AC I got the square root of 18, and for CB I got square root of 32. So I just multiplied the square root of 18 times the square root of 32 and got the square root of 576, which is 24 divided by 2 is 12.
Okay, good. So you found the two sides. Let's see. So one thing this might have assumed is that this triangle was a right triangle, that you could multiply the sides. So you found the two side lengths, right?
Yeah.
Okay. So yeah, I think this did assume that it's a right triangle, so you can multiply the sides. But yeah, in this case, it did work. But let's see how you could do it without that. So did anyone do it a different way?
I use the shoelace theorem.
Good. Yeah, shoelace is one way. How do you?
Okay, so what I did was I wrote the points in this order vertically: 2, 6, -5, 5, -2, 2, and 2, 6.
And why did you pick this order?
Because that was the way that so from the point that you start, you have to like move left and pick and continue using the points.
Good. Yeah.
Okay, so then first you kind of have to like cross multiply. So it would be 2 times 5, and then you do 10, and then minus, because the one going from the right to the left multiplying, you always have to put a minus first. So then it's 10 minus 30. And then the next one, using the same way, is -10 minus 10. And then the one after that is -12 minus 4.
Good. Yep.
And then once you add up all those, you get 24. And then you have to do 1/2 times 24 to get 12.
Good. Yep. Okay, let me write this out and then we'll go through it once. Okay, so this method is called the shoelace method, and for if anyone has not heard of this method, it's particularly for if you're given the coordinates of a triangle or of any polygon with the locations of each vertex, you can use this method to find the area. So it's kind of a trick for when you're given these coordinates, but it works nicely when you have this. And the way you do this is first you start from some vertex in your in the polygon. So it could be a triangle, it could be anything else. In this case, Preeti started from 2, 6, this point, and then you want to move counterclockwise on the polygon. So in this case, that would be then to this point, A, -5, 5, and then to the last point, -2, 2, and then to B. So in this order, you want to write the vertices in this kind of list. So you start with B, 2, 6, then -5, 5, then -2, 2, and then the same starting point again, 2, 6. So you write it in this format. And now the trick is, so this kind of crossover adding looks like a shoelace. So that's why it's called the shoelace method. And what you do is you first start off with taking this product, 2 times 5. So you kind of the first diagonal in a sense. You multiply those. Then you add to the next one, -5 times 2. You add it to what you got before. And then -2 times 6. You add these up and you get -12. So if you had more vertices here, you would just continue the same thing. You'd multiply in this fashion and add them up. And then the other direction, you take 6 times -5, 5 times -2, and 2 times 2. So again, you do the same thing. You get this product, and this product, and add them up. There you get -36. Now the last step is to take -12, the first one, subtract the other one, -36. If you get a negative number here, you have to take the absolute value. And then just divide this by 2. And you get, in this case, the area of 12. So this trick works for if you know the coordinates of any polygon. So it does take a little bit time to get used to doing this method, but it's called the shoelace method or theorem, shoelace method, to find the area. Does this method make sense? Okay, did anyone do it any other way? Okay, so one more method of doing this problem, other than the shoelace approach, is you could actually just imagine that we took, so if this was not a right triangle, then just from the side lengths, we wouldn't be able to find the area directly just by multiplying. But what we can do is we can kind of construct this rectangle around the vertices here. And the nice thing about this is that once we have the rectangle, we know the side lengths, and we can just subtract these 3 right triangles outside of it to get the area of this triangle. So now let's see what these lengths should be. So from the coordinates, we know this should be 3, this should be 4, this is 4, this is 7, this is 1, this is 3. So now we can find the area of this triangle, and this triangle. So this triangle area is 8. This triangle area is 9/2. This triangle area is 7/2. And we can subtract these from the area of the full rectangle, which is just 7 times 4, 28. So it's 28 minus 8 minus 9/2 minus 7/2, which gives us 12. So same answer, but you can do it in this way. Or the first method, if you confirm that this is a right triangle, so if you check that this is perpendicular to this, then you can also find the length and multiply it in the first method that Ishan gave. Okay, so there's a few methods of doing this, but we all get the same answer of 12. Does this make sense? Any questions? Okay, let's move on to the last question. Okay, good. 185 is the right answer. Sanvi, can you explain?
Okay, so I took 5,000, and so if 0 was in the hundreds place, there would be 6 options. If 1 was in the hundreds place, there would be 5 options, and so on. And so when you add 6 plus 5 plus 4 plus 3 plus 2 plus 1, you get 21. And I continued the same thing for 6,000, except instead of starting with a 6, I started with 7 plus 6 plus 5, and so on. And for 7, I started with 8. For 8, I started with 9. For 9, I started with 10. And you get 21, 28, 36, 45, and 55. And when you add all these up, you get 185.
Good. Yep. So one way of doing this is you can actually check in each for each thousands digit. So in the first case for 5, you should get 21. Then you can repeat this for 6, in the 6,000s. So then if you have a 0 in the hundreds place, you can get and see that there should be 7. So 7 here would be, if 0 is in the hundreds, it could be the tens digit could be 0, 1, 2, 3 up to 6. And then the unit digit is would be the remaining to make it equal to, in this case, 6. And so on. So you can add up these values and so on. So this you get 7 plus 6 up to 1. You get 28 here. The 7,000s will get 8 plus 7 plus 6, so on. You get 36. 8,000s, it's 9 plus 8. This is 45. And the 9,000s is the last one that would be, so if there's a 0 in the hundreds place, then there'd be 10 choices for the tens digit, anything of 0 to 9, and so on. And this would be 55. And then we could just add these up, 21, 28, 36, 45, 55, and get a total of 185. Okay, so this works. It's a little bit more computation to make sure we count everything for each case and then add these up. But we get the right answer here, 185. Any other methods of doing this? I see a few other people got 185. Did anyone do it a different way, or everyone did it this way?
I did it this way.
Okay. Okay, so let's discuss another way of looking at it. So we've discussed this method a few times before, the stars and bars method. Any ideas of how this could be applied here? So when I have a first digit of 5, I want my remaining digits to add up to 5. So basically, I want 3 numbers that add up to 5. So all the possible choices, let's say like 0 plus 1 plus 4, 0 plus 2 plus 3, and so on. 2 plus 3 plus 0, order matters, right? So this is essentially, if I think about it in the stars and bars method or ball and urns way, it's like if I had 5 dots, 5 balls, and 2 dividers. So I want to divide these 5 into 3 groups. So let's say I would put 1 divider here, 1 divider here, that would say 1, 3, 1. Alternatively, if I had the 2 dividers next to each other, this would be 1, 0, 4. So basically, I have a total of 5 dividers and 2 objects, or 5 balls or 5 dots, 2 dividers. So I have 7 total items, and I want to choose the 2 locations of the dividers. So with the 5 in the first position, to choose the number of ways of filling the next 3, it would be 7 choose 2, which is 7 times 6 over 2, which is 21. And this matches up with the same 21 that you could count here with a 5 in the first place. So we can just kind of extend this and say, okay, so 6 dots and 2 dividers when there was a 6 in the first position would be 8 choose 2 instead of 7 choose 2. So basically what we then want is 7 choose 2 plus 8 choose 2 plus 9 choose 2 plus 10 choose 2 plus 11 choose 2. This happens to, this is the same thing as what we counted here of 6 plus 5 up to 1, 7 plus 6 up to 1, and so on. So 7 choose 2 would be 21, 8 choose 2 is 28, 9 choose 2 is 36, and so on. So this is a little bit simpler maybe to get to this point of which things you need to sum. If you think about it in this way, and you can get just this expressions for each of these. Now the last step is actually then computing each of these and adding it up. Does anyone know of a potentially easier way of adding these up? 7 choose 2, 8 choose 2, up to 11 choose 2. Any ideas? Okay, so there's something called the hockey stick identity. This is a little bit more advanced, but I'll just give a quick summary to just as an idea of how to do this more easily to compute this sum, especially if it was a larger sum. So when you think about permutation or combinations, one thing that kind of represents these is called the Pascal's triangle. And this shows essentially like starting with 1, 2, 3, and so on. If I say 0 choose 0, 1 choose 1, like all of these values are all represented in this triangle. So let me put a few rows here. And the nice property of this triangle is that every number is the sum of the two numbers above it. So this is an interesting thing to look up if you haven't seen it before. 6. Okay, so this triangle, if you see, like, let's say we choose this row, right? So the values here are 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. Same with any row I pick is the some number choose 0, 1, 2, 3, and so on. So one property is that any number is the sum of the two values above it. There's also one interesting property is if I pick values like this, like along this line, let's say this 1, 2, 3, 4, their sum is actually this value, 10. So if I draw this, so if I take 1 plus 2 plus 3 plus 4, it adds up to this 10. And if I look at this kind of figure, it looks like a hockey stick, right? If I added 1, 2, 3, 4, that's sum to 10. This looks like a hockey stick, so it's called the hockey stick identity. And I can double check that this works for any other line. So for instance, if I check 1, 3, 6 here, it adds up to 10 here, the same way, and so on. So if I look at the ones that, so like 7 choose 2, 8 choose 2, 9 choose 2, that's like kind of some of it incomplete. It's not starting off at the beginning. So let's think about, let's say I did start from 2 choose 2, 3 choose 2, 4 choose 2. So which line would that correspond to here? So 2 choose 2 should be here, 3 choose 2 here, 4 choose 2 here, 5 choose 2 here, and so on. So we can see that the same kind of trick works in this direction also, right? 1 plus 3 plus 6 sums to 10. So the nice property here then is that, so if I take 2 choose 2 plus 3 choose 2 all the way up to 11 choose 2, this should actually equal to, so if I look at what this should be there, it should be 12 choose 3. Now I don't really want to start from 2, right? I only want to start from 7. So I can take 2 choose 2 plus 3 choose 2 up to 6 choose 2 and subtract it from the original, from the total sum, and that'll give me exactly the 7 choose 2 up to 11 choose 2. The 2 choose 2 up to 6 choose 2 should then be with the same trick, 7 choose 3. So my final answer should just be 12 choose 3 minus 7 choose 3. So this is a little bit more advanced to think about, but if you know these tricks, you don't actually need to compute each of these and add them up. You just get these two things, which you can then compute and just subtract these two values. So this makes it even easier if you had to add up a larger sequence, but this trick can be useful when you're trying to add up combinations that are in a sequence like this. So if you haven't seen this before, look up the hockey stick identity and Pascal's triangle. And this also reviews the stars and bars method that we had discussed before. Any questions on this? This will result in the same answer that we got here, the same 185 of adding up these values. But this is another method of getting the same thing. Any questions? Okay, that's it for today. We'll see you all next week.
Thank you.
Thank you.
Thank you.
Thank you.
You're welcome.